Type of compound. This is what we did it. We produced these short peptides with the carboxylic and the diamine functionality. We can ligate this peptide by cyclization to near infrared dyes for tagging these molecules. We can ligate it to polyether change if you want to incorporate cations. You can play around a little bit, and then you can find this. You can produce this amazing molecule which unfortunately have no application by now. So this is somehow everything I wanted to tell you today. My idea is just to highlight how you can use a simple reaction like this, a multi-component reaction, in amazing type of synthetic chemistry. Some of this chemistry is true, that it's just to play around a little bit, but some others actually we apply for the synthesis of bioactive compound, of antibacterial or anti-cancer compounds. These are my students. You know that very well. This guy is in Germany doing the PhD now by this project, like this one. This guy probably comes next year if we get accepted our project finally. And this is my IC students, which they are amazing. They work more than the PhD students. I have to thank to these two professors, Besjohan and Westerman, because they support all of my ideas. They give money for my research. I can send the students almost to do whatever I want in Germany. So I am lucky in that sense, because in Cuba sometimes it's difficult to do. To the Canadian Center of Cancer Research for the biological evaluation, to the people who do the solid phase peptide synthesis. Sometimes I get these peptides from the machine. I don't have to produce it, and this is easy. You really have to think to implement something about here, one of these synthetic machines. And finally, I would like to spend 1 minute, I think I have time, to make like a summary of my stay, of my visiting professorship stay. The main objective of my stay here, as you know, I am a specialist on multi-component reactions, not new by now, was to set up at this department a combined multi-component catalysis program for the development of new synthetic tools, strategies, methods, whatever. So we really want to combine the power of multi-component chemistry with the power of organocatalysis in the generation of enantiomerically rich molecules to produce bioactive natural products, to discover new type of catalyst or catalytic system. That was our idea. I think we had some success. My friend will say if I was useful or not. We started a co-orientation of a PhD student on this topic, the multi-component combinatorial discovery of pseudopeptidic catalysts, so using the diversity-oriented capacity of multi-component reaction to discover new pseudopeptidic catalysts. We had the news that we got approved a CAPES cooperation project with Cuba. This will allow us to keep the students coming here half a year, sequentially, one after the other one. Also, we are giving a postgraduate course of 25 hours with Marcio on the field of multi-component reaction. We have 4 articles planned for this. 2 of them are already ready. One, if approved, is on the Gali proof stage already. 3 of them are expected to be I1. So it's good for the faculty also to increase the level of the publication. And probably this is the most important. Marcio is a great friend of mine. We studied together. We are like brothers. But we never had the chance to join our chemistry. I think now we have it, and I hope we have great success. Finally, I want to thank again to my friend Marcio, to Arlene for everything I said before, and also to Ernesto for the acceptance at the Department of Chemistry, because actually nobody knew that if I was going to be useful for this department or not. I hope I was, and I hope you allow me to come again. Okay, and to all of you for your kind attention. Thank you very much.
Primero, parabéns pela apresentação. Apesar de não ser realmente minha área, é extremamente interessante. Entonces, eu queria fazer uma pergunta, na verdade está relacionada com a slide 35. Aí hablaste de los criptandos, y la posibilidad, especialmente, la idea de poder incluir dentro cátions o cualquier otra cosa.
We try to co-crystallize some cations with this, but
it's in English. So
No, disculpa.
To the slide 18, which is, again, it's not a cryptography.
18.
Sí, 18. Yeah, on the right hand side or in the top, all this kind of, this kind of compound. You have space there also with the 6 oxygens in the middle. So you cannot put.
We are not sure. It's just a way of representation. It's only a way. It's tricky. It's only a way of representation. Actually, the more accurate way to represent is like this, because here we are putting the amide bonds like sometimes they get cis or something.
So there is no room.
No, we don't know. Actually, we got inspired by the valinomycin. It's a cyclodepsipeptide, which there is X-ray with there is a place for cesium and potassium in the cavity, I think is. But for this, I think they are too small. Probably they are too small for putting a cation here. I don't know if lithium or sodium. I don't know. But this is amazing because it's well known that the carbonyl peptides, they coordinate with cations. All the membrane crossing of sodium and potassium is all by coordination with the carbonyl groups of proteins or something like that. And there are natural products which derive the biological activity by the encapsulation of cations. This is, you are right, this is. It's completely no, but we don't know, Professor. This is just a way of representation, I have to say. We only have enhanced now the synthesis and the NMR study of this type of compounds. I really put it like this because now we demonstrate that we have a hydrogen bonding between this carbonyl and this proton and this amine here. So we have like a Thorne motif here, which is easy to understand when you take a look to the size of the asteroid. So it really folds the molecule to make like this, to make like a Thorne. Now we are preparing with a methyl with the different sizes just to prove what is the percentage of the Thorne motif in the molecule. But then we get one-to-one mixture of conformers, and it's difficult. With the asteroid, the molecule is fixed to be Thorne like this. And actually, these molecules cyclize better than this one. In this example, it's not a good example, but we find because this Thorne motif oblige the molecule to make like this, so the cyclization is easier because the molecule already has this conformation. In this case, this branch peptide is not so easy. Although this example probably is not the best one because this amine here is axial, so there is other type of steric interaction with the asteroid because it's axial in this case. But with the equatorial ones, they cyclize amazingly well. We found that. For example, in this one cyclize very well, even if it is a pentapeptide. But this chemistry, I said many times that it's very easy in multicomponent. This chemistry is not easy at all. So this one is very tough. So the Uris reaction are easy, but this one is not at all. Yeah, the others are just to mix and to make the column, but this one, no, actually, no. It's very tedious, the preparation of this intermediate. And this peptide, we did it in solution phase, so it's coupling after coupling. But anyway, it's known chemistry.